If the satellites should communicate between them, it means that the communication in space needs to be done in a certain manner. And now I'm coming to the central point of my presentation. And this is being done using laser communication. So it is not radio frequency anymore like it was before. It is an optical communication between the satellites. The point is that the space isn't exactly a friendly environment. The space is a really nasty environment. And in this really nasty environment, the main problem that we have is in fact the radiation. But there is a circuit, and I'm going to talk about this because this is the main topic. There is a circuit, and these circuits are the ones realized in silicon photonics. Now, because of the very nature of the way these circuits are being realized, they are immune to radiation. And this is a huge advantage that they bring. Well, after discussing this concept of what is the new space and where this one applies, let's look a little bit at the contribution that we are bringing it. In fact, we do two different things. First of them, we develop the technology to take circuits which are being used for the modulation of the communication signals. We are developing the circuits, and for this one, we are developing the flip chip technology. Why is this flip chip technology so interesting? Well, simply because it is a technology which is not low cost. It's somehow exaggerated to say low cost, but it is definitely a technology in the range of technology having the cost advantage, clearly. The second thing that we are developing, and we are progressing on this one, is we are going to develop the technology to assemble and make silicon photonics circuits resilient to space. And this is definitely not a trivial activity. First part, let's talk about this flip chips. So what you are doing is we take circuits in the 22 nanometer technology, and we develop all the processes necessary from the wafer to mount an flip chip in a non-hermetic way. So it's going to be a non-hermetic flip chip using soldering as an activity. The technology is going to be proven to work according to the very hard stress environment in space. So there are several standards that apply in this case. That is the ESCC 90 and the MIL 803. They are absolutely rough way of testing circuits. Once we get this one done, then we go to the next stage, and the next stage will be having large circuits developed for use in space. One single circuit, the way it's being done right now, has something like 700 connections. A large circuit having a size of 20 times 20 millimeters will have more than 11,000 connections. And we are going to test all these connections for continuity, but we are also going to test them for the radio frequency behavior. In other words, these circuits will be used for the modulation of their communication signals, and they should better be able to behave nicely up to a couple of gigahertz. To this purpose, we developed a lot of investigation elements. That's the way they look like, and they are going to allow us to perform the radio frequency evaluation of the circuits. Now I'm moving from this part because any kind of optical circuit needs to be fed with information, and this was the way we are going to feed it. Now I'm moving from that part to the part which is related to the silicon photonics. Once again, because of the very nature of the way the silicon photonic circuits are being produced, they are immune to radiation. And this is a huge advantage when talking about sending devices into space. What are we going to do? We have sufficient technology to make all kind of very nice alignment, being passive alignment, where we are right now in the range of 200 nanometer of accuracy for placement, but also optical active alignment, which is being in place at our factory right now. So we really know how to make this silicon photonics circuit and assemble them. But the next stage is going to be taking the circuits and once again subjecting them to the same level of very hard test, of very harsh environment test like the flip chip circuits. At the moment when this is going to be achieved, what are we going to have? We are going to have a batch of processes that will allow us to take existing circuits or circuits which are going to be newly developed and mount them and assemble them in a way that can be used in swarms of satellites to be sent into space. This whole project, or these whole projects, in fact, they are being done by us, of course, not alone, but it's a very strong cooperation with the ESA, the European Space Agency, with the French and the German state-controlled institutions, CNES and DLR, and with other partners in the industry or in the testing industry. So the result is going to be, and what I'm talking about is going to be end of 2022, so end of next year. The result is going to be a set of processes mastered, well controlled, well understood, that would allow us to build systems in package whereby silicon photonics can be integrated with traditional flip chip, soldered flip chip, and be ready to use in space. So this is the message that I had for today. We are getting these technologies ready, and the huge advantages of the silicon photonics are going probably to make this technology extremely interesting for space application. So it's a short presentation. If you want to know more, we are having a series of webinars that we're holding at AEMTEC. You are absolutely invited to join us, where we are going to talk about the different technologies in details. For any kind of questions, it's info@aemtec.com or dan.negrea@aemtec.com, and this presentation will be, of course, available online.